Hi everyone, this is Mrs. J, and today we're going to talk about independent events. So first I have a little warm up for you guys, so please pause the video and give it a try. Alright, go ahead and check your work here. So remember, you can use the totals going across the rows, or the totals going down the columns, or the totals in like the final column or the final row to help you kind of work your way backwards to fill in the missing boxes for any two-way frequency table. All right, so again, today we're going to be talking about what are called independent events. So we're going to start just by looking at this general example. So this says a jar contains 15 red marbles and 17 yellow marbles. You randomly draw one marble from the jar and let event R be the event that you pick a red marble, and let event Y be the event that you pick a yellow marble. So first we're going to find the probability of R and then the probability of Y. So for the probability of event R, again, there are 15 red marbles, and then you can see that there are 32 total marbles. So the probability of picking a red marble is 15 over 32. Now let's find the probability of drawing a yellow marble. There's 17 yellows, 32 total, so that's the probability of drawing a yellow. All right, let's move on to part B. So in part B, we pick a marble, and the first marble we pick is red, but then we put that marble back in the bag before we pick a second marble. So let's find the probability that the marble is yellow, given the probability that we already drew a red. So in this case, we're still going to look at the number of favorable outcomes. So there are still 17 marbles in our bag when we go to make our second pick. And since we had put that marble back after the first pick, our total number of outcomes for the second pick is still 32. So you could see that in this case, because we put that marble back, the probability of Y given R is just the probability of Y. And again, that's because we put the marble back, so the total number of outcomes was still the same, and the total number of favorable outcomes was still the same. Now let's look at part C. This says, suppose the first marble you draw is red, but then you don't put it back before picking a second. So find the probability that the marble is yellow, given that we picked a red. So in this case, again, if we look at favorable outcomes, there are still 17 marbles to pick from. However, the total number of outcomes and for the second pick has changed because we have taken a marble out. So in this case, there are only 31 total outcomes. So the probability here, when we don't put the marble back, is 17 out of 31. So you can see in this case, the probability of Y given R is not the same as the probability of Y. So here we have two examples of two different types of events. Here, this was in part B, this would represent what we call an independent event, because what we do on the second pick, or what we did on the first pick, had no effect on what we did on the second pick. So those two events are independent. But if you look at part C, what we did on the first pick did affect what we did on the second pick, because it affected our denominator, right? So we would not call these events independent. Because again, today we're talking about independent events. So here's one way we can describe independent events. So again, independent events is when the occurrence of one event has no effect on the occurrence of another. So for example, another example of an independent would be flipping a coin and rolling a dice at the same time. Whatever you do with your coin has absolutely no effect on the result of your dice, so those are two completely independent events. So if two events are independent, the probability of event A given B is just going to be the probability of event A, as we saw in the last example, because the first event, or the conditional event, event B, has no effect on A because they are independent. So this is true if you know that the events are independent. So here we're given a two-way frequency table. We've seen this before in a previous notes, where we have domestic and international flights and then late and on-time flights. So here we're asking, is the event that a flight is on time independent of the event that a flight is domestic? So we're going to actually use that fact that we just learned, that if two events are independent, so if they're independent, we know that the probability of A given B should just be the same as the probability of A. So we can actually use this to determine if two events are independent. So if they are independent, then this should be true. So let's see, this says, is the event that flight is on time, we'll call that event A, independent of the event that the flight is domestic? We'll call this event B. So let's find the probability of A given B, and then we'll find the probability of event A, and we'll see if they are equal, and if they are equal, then the events are independent. So to find the probability that event is on time, given that the event is domestic, so remember here we're only looking at the domestic flights, so the total number of domestic flights is 120, that's our condition, and the total number of on-time flights that are also domestic is 108. So it'd be 108 out of 120, which is a probability of 0.9 or 90%. Now let's find the probability of just event A, which is the event that the flight is on time. So if you look at the total number of on-time flights, it's here, and then the total number of flights period is 180. So to find that probability, again, the favorable outcomes is 162, total outcomes is 180, and again, if you find a decimal for that, it is also 0.9. So since P of A is equal to P of A given B, we can say that these two events are independent. So you can see that the condition of the flight being domestic had no effect on the flight being on time. Now let's look at part B. So here this says, is the event that the flight is international, we'll call that event A, I'll do it in red again. Is the event that the flight is international independent of the event that the flight arrives late? So we'll call that event B. So again, let's find probability of A given B and then compare that to just the probability of A. So let's start with A given B. So in this case, let me erase here. In this case, the condition is that the flight arrives late. So there are 18 flights that arrive late. And then we're finding that the probability of the flight is international, so that'd be 6 of them. So it's a 6 out of 18. So the probability there is 1/3. And now let's just find the probability that the flight is international. So there are 180 total flights. And then if you look at the total number of international flights, it's 160. So we'll do, just 60. We'll do 60 over 180, which is also 1/3. So again, since P of A given B is the same as just P of A, we can see that the condition of the flight arriving late had no effect on whether or not it was international. So these two events are independent. All right, so I have one for you to try on your own. So please pause the video and give it a shot. All right, go ahead and check your work here. So for this first one, again, if you find probability of A given B, so for one bedroom, there's 90 outcomes and 64 of them are single occupancy. So that's 64 over 90, which is about 0.71. And then the probability of just being single occupancy is single is 76 over 200, so 0.38. So those probabilities are not the same, meaning the events are not independent. And then for the second one, probability of A given B, multiple occupants there's 124 total outcomes and 98 of them are event A, 2 or more bedrooms, so 98 over 124. And event A, just being 2 or more bedrooms, is 110 over 200. So these two probabilities are not the same, so the events are not independent. So if you are finding the probability of independent events, the probability of the intersection of A and B, if they are independent, is simply the probability of event A times the probability of B. So remember when we were doing probability of A or B, we added the original or the individual probabilities. When we're doing A and B, we multiply. So and is multiply or is add. So this is how you find the probability of the intersection, but it's also a way that you can check to see if two events are independent. So events A and B are independent if and only if this is true. So in the previous examples, we checked the conditional probability to see if the two events are independent, but you can also see if they're independent by multiplying the individual probabilities and see if that's the same as the probability of the intersection. All right, so let's give this next example a try. This says a bag has 12 apples and 9 oranges. Suppose you draw a fruit randomly from the bag, put it back, then randomly draw a second fruit from the bag. What is the probability that you draw an orange first and an apple second? So since you're drawing a fruit and then putting it back, what happens on the first pick actually has no effect on what happens in the second pick, because you still have all of the things to pick from and you're just as likely to pick any of the fruits. So to find the probability of A and B, where A is, we'll call event A drawing an orange first, and event B is drawing an apple second. And we know that they're independent just based on the scenario. So to find this probability, we simply find the probability of picking an orange, and we multiply it by the probability of picking an apple. So for this, well, there are 9 oranges, and there are 21 fruits total. And then we're going to multiply that by the probability of picking an apple. So 12 over 21. And again, these two events are independent because we are putting it back. So you see like the total sample space is unchanged. And again, just because you picked an orange first, it doesn't really affect what you're picking second. So you're just going to multiply and simplify. And you should end up with 12 over 49 after you simplify. All right, let's try another one together. So here we spin the spinner that's shown below 2 times. What is the probability that the spinner stops on an even number on the first spin? So we'll call that event A, and followed by an odd number on the second spin. So in terms of this scenario, these two events are completely independent because, you know, whatever I do on the first spin has absolutely no effect on the outcome of my second spin. So if I land on an even number the first time, that doesn't mean that I take out those numbers and I can't add on an even number, or whatever number I do land on, we don't remove it from the spinner, right? So every time I really have, it's a unique event. So really what I do first has no effect on what I do second. So to find the probability of that intersection, I simply multiply the 2 individual probabilities. So first, the probability that we hit an even. So we can see that there are 3 even numbers, 6, 8, and 12. So 3 out of 8 total numbers. And then we're going to multiply that by the probability that we hit an odd number. So there's 1, 2, 3, 4, 5 odd numbers, again, out of 8. And then from here, all you need to do is multiply and simplify if necessary. In this case, you don't need to. So the probability is 15 out of 64. All right, so I have one for you to try on your own. So please pause the video and give it a shot. All right, go ahead and check your work here. So these two events are independent because what you get on the first term doesn't change your spin on the second term. You have the same spinner, the same possible outcomes, the same total outcomes. So they're independent events. So you find the individual probabilities, and because it's the probability of A and B, you multiply those probabilities. So it's 2 out of 10, which is the probability of spinning a green, and 3 out of 10, which is the probability of spinning a blue. And again, you add up 4, 3, 2, and 1 to get you that denominator of 10. All right, I have another one for you to try on your own. So again, please pause the video and give it a try. All right, so go ahead and check your work here. So again, the first roll and the second roll are independent events because what you roll on the first time doesn't take away options for the second one or doesn't change the possible options because the dice stays the same. So I called event A an odd on the first roll, event B is an odd on the second roll. Each probability is 2 out of 6, so you multiply those to find the probability of both, and you get 1 out of 9 when you simplify. So now that we know another way to kind of define independent events, we know that if, again, the product of the individual probabilities equals the probability of the intersection, then they are independent. We can also use this to help us show that two events are independent or determine whether or not they are. So again, this time, instead of using a conditional event, let's try to see if we can prove it using this. Because remember, two events are independent if and only if this is true. So this says, consider this two-way frequency table, determine whether a patient who takes vitamins, and a patient who exercises regularly are independent events. So if they are independent, the probability that a person who takes vitamins times the probability of a person who exercises should equal the probability of a person who takes vitamins and exercises. So let's start by finding the probability of a person who takes vitamins. I'll call that event A. So this is event A. So the probability of a person who takes vitamins, I can look at the total number of people that is out of 120. So that's 60 out of 120, so 1/2. Now let's find the probability of a patient who exercises regularly, which we'll call event B. So I can look at regular exercise. There are 76 people there over 120. So 19 over 30. And then let's find the probability of the intersection of A and B. So if you look at your chart, there are 48 people who take vitamins and exercise regularly. So the probability of that is 48 out of 120, which gives you 2 out of 5. So now we have to see if the probability of A and B is equal to the product of the two individual probabilities. So we're wondering, is 2/5 equal to 1/2 times 19/30? Well, we know that 2/5 is not equal to 19 over 60. So since they are not equal, we can say that these two events are not independent. So again, two events are independent if and only if the product of the individual probabilities is equal to product of the intersection of the two events. All right, now let's try another one together. So now we have a different set of data about kids that whether or not they know how to swim and whether or not they know how to ride a bike. They're wondering, we're trying to determine whether a child who knows how to ride a bike and a child who knows how to swim are independent events. So we'll call this event A here and event B. So we're going to find the individual probabilities first. So the probability that a child knows how to ride a bike would be 45 out of 60. So 3 out of 4 probability. Now let's find the probability that a child knows how to swim. So that's 40 out of 60. So 2/3. And now we're going to find the probability of the intersection. So how many children know how to ride a bike and know how to swim? That'd be 30. So 1/2. So I'm wondering, again, if the probability of the intersection is equal to the product of the individual probabilities. So is 1/2 equal to 3/4 times 2/3? 1/2 is equal to, this becomes 1/2, 2/4 is 1/2. So since this is true, we can state that these two events are in fact independent. All right, so here's one last one for you to try on your own. So please pause video and hit play when you're ready to check. All right, go ahead and check your work here. So I found the probability that a plant is sprayed with insecticide. So 52 out of 80. The probability that a plant has aphids is 26 out of 80. And then the probability that it has both aphids and has been sprayed is 12 out of 80. So you can see that the product of A and B, of the probabilities of A and B, is not equal to the individual probabilities product. So that means that these two events are not independent. Okay, that is all for today's video. Thank you so much for watching.